Hello everyone, I'm Ryan Erickson. Today I'll be talking to you about building products faster with Zephyr and MicroPython. I'm with Ezurio. I've been with Ezurio for 15 years now doing wireless products, and our company has actually been around for over 40 years developing products and wireless products now. I want to highlight our new company name. We were formerly Layered Connectivity. We're now Ezurio. We do wireless modules, IoT products, and all that. So please check out our website. It explains why we changed our name. You can talk to me after too. I can explain a little more. But all right, today we're going to go over what Canvas software suite is and how that plays into MicroPython, all our supported products, and then we'll get into the good stuff about how we made this happen. So first, what is Canvas Software Suite? Canvas Software Suite is our software platform for enabling rapid portable development across all our microcontroller-based products. First is the firmware, which is where the Zephyr and MicroPython come in. We have a set of tools that helps users work with that firmware on the product. Of course, there's samples, and then documentation like API documentation and all that good stuff. So first is the firmware. We have many platforms out there. I'm going to talk more about what those hardware platforms are in the near future here. A lot of my slides will have links, so you can get to all the reference material pretty easily. After the presentation, you can download the slides and all that. Along with the firmware, we have a set of tools. First, the most important and user-facing one, I would say, is our Visual Studio Code extension. This allows users to create, load, and interact with Python code on the device, as well as editing your Python code and running it. You get access to the Python REPL through the terminal interface in VS Code. So that's really nice because it's cross-platform. We also have a desktop application, and why that's important is we'll have certain firmware that runs on devices, and we want to be able to demo and show stuff off in a graphical way. So our desktop app allows us to write JavaScript-based applets very quickly to visually represent data as we need. And this also allows our customers to do the same. In the future, we'll be creating more documentation and make it more clear on how users can use that desktop app to build out and really quick proof of concepts. We also have a mobile app that effectively does the same thing as the desktop app, runs the same exact applets, just on a mobile platform. So that's really nice when you need something smaller. And also, it's nice for being able to do over-the-air updates to our devices. And then, of course, samples. We have all our Python samples out on GitHub, and we're continually adding to them and updating them. And last but not least, the main website, where it collects all our documentation and gives you the overview of the platform. When you have time, I highly recommend checking out the website here and watching our little overview video. So what products are supported from our portfolio? A lot of them. We are able to bring this up in a relatively short time because of Zephyr. All of our products contain BLE. But I'm going to touch on a couple of the more unique ones. Our newest product is our Sarah NX040 in the top left here. That's our BLE plus UWB module, which allows really accurate locationing. So that's really cool, and I'll be touching on some more of that throughout the presentation. And then also our Centrius MG100 gateway. So of course it's got BLE, but it also has cellular, so you can get your BLE data to the cloud. So some of the sample apps, I got them grouped here by platform to kind of highlight some of the main features. Of course, all of them, as I mentioned, have BLE. So any BLE you write in Python on one will work the exact same on any platform. So that's really handy. Our UWB module, we have a ranging demo that will talk to a tag, will talk to 3 endpoints, and with our desktop application, give you a 3D location visualization in a room. So that's a pretty cool demo. And then our gateway, we have our BLE to MQTT sample that people can customize for their needs. All right, now I'll get into the architecture here on how we built this and made this possible. So it all starts with MicroPython. For those of you who don't know, MicroPython is an implementation of Python 3.x that is designed to run on microcontrollers. MicroPython provides ports for different embedded systems, and a port could be based on an RTOS or it could be a bare metal based port. MicroPython provides the source for all the core subsystems that are used, for example, file systems, networking, USB, and many of these subsystems are based on other open source projects. So similar to Zephyr, they're pulling in these other pieces of source code to build upon. One of the problems as you look through some of these ports is many of the ports vary on how complete they are. They'll give you some features, but maybe not fully everything you want, and some of them are not well maintained. Another thing is when building a final product, firmware updates are very important. I'm going to mention that several times today, but I think we can all agree in this day and age, if you don't have firmware updates, you're not going to have a product. So that's why I'm going to stress it so much today. So we first took a look at the MicroPython NRF port. This port is quite outdated. Its BLE subsystem is based off the old NRF5 SDK, which is their soft device. So, Nordic has now moved on to NRF Connect SDK, which is based on Zephyr. So right away, when you look at something like this, it's like, it's not worth using, right? It's no longer supported by the vendor. You're going to have problems with Bluetooth qualifications. When you do an end product, these certifications and qualifications are needed in order to sell your product. So there's no RTOS benefits, and of course, you'd have to manually add all the features you want yourself, which is a lot of work. Next, MicroPython has a Zephyr port. This is getting close to what you would want, but there's a few things that aren't ideal. First of all, it's not up to date with the latest Zephyr. Now, sometimes being up to date doesn't mean everything, but it is nice to be able to be somewhat up to date so you can pull in new features as needed. It doesn't leverage all of Zephyr's subsystems. It uses its own virtual file system. The BLE features are not fully featured, and this is because of lack of, call it a Python glue layer for gluing the BLE APIs in Zephyr to the MicroPython subsystem. For example, there's no extended advertising or scanning. You can't use all the PHYs. And again, they're not taking advantage of the bootloader firmware update support that Zephyr can give us. Just going to touch on this quick. Can't talk about architecture without a stack diagram like this. So just to highlight, on bottom right here, at the lowest level, we got our vendor SDKs and libraries. In this case, Zephyr's kind of sitting there for us. And then at Ezurio, we've developed some layers here, which we call our platform middleware. And that's allowing us to kind of abstract APIs from the scripting engine which lies above it. And the reason this is important is in case We do have a product that doesn't support Zephyr, which we unfortunately do with a couple of our modules because they're based on a silicon that's not fully supported in Zephyr yet. So that's where developing those extra layers benefits us, so we can still build MicroPython for them and have it work the same way. All right, so now we'll get into Canvas MicroPython, right? So the difference here compared to how I've seen everyone else do it is Zephyr is the core. So we build Zephyr first, and MicroPython has been added as a module. So because of this, we can benefit from all Zephyr's features. Their fully qualified Bluetooth stack, which is very important, networking, security, all that. And then we bolt MicroPython on with a thread. So first, here's a little snapshot of our manifest where we're adding MicroPython pieces, pulling them down. And here's a little quick snapshot where we're using sysinit to, on boot, start MicroPython up in a thread. So we were able to do this because MicroPython has what they call an embed port. The embed port is designed to embed MicroPython in any other existing C application. So we use this to our advantage because we were able to then turn that embed port into a Zephyr module. Also, in case you don't have Zephyr, it will work as well. So the first thing we got to get working on the device is a file system. It's one of the most important things with a MicroPython device. If you don't have a file system to store your Python files, you're not going to be able to do anything that's useful. So in Zephyr, with kconfig and device tree, you don't have to write any C code to get a file system running on your board. With kconfig, turn on the file system and pick what file system you want to use. In this case, we usually always use little fs. And then on the right-hand side here, you can see a snapshot of our device tree where we have a partition set up in an external QSpy, and then we use fstab to boot and auto-mount that partition. You can see the auto-mount flag right here. So it's linked to this file system partition, and on boot, it boots up and formats it if it's not already formatted, and you're on your way. You got your file system already running. Now the file system's running in Zephyr, we got to connect it to MicroPython though. So we had to implement a new module. We call it Zephyr MicroPython, and the purpose of this module is so we can glue Zephyr APIs into MicroPython. On the left-hand side here, you can see several of the different ones that we've done. Platform FS is for our file system, so that's what I'm kind of talking about right now. We've had to do some work with networking, time, and some UART stuff. So for the file system, the first thing we needed to do is implement the open function. This function is kind of special because it's the first thing that you need to do in order to get access to a file object, right? Everything in Python's an object. So this is the call into the Python framework, linking it to our open function, where then we call our Zephyr file open. Once you have your file opened, you need to be able to read and write to files. So MicroPython implements streaming functions, and they treat a file as a text file or a binary file. So this is showing the macros that are used in order to marry up the Zephyr API calls with the MicroPython system. So whenever you open a file, you have to implement your read, write, and I/O control streams, and that's, you can see here where we're linking into our specific Zephyr file read and file writes. And also, since we're using Zephyr, we get to use the Zephyr driver architecture, so that's pretty fantastic when you need to add some new hardware. We don't have to think about how to do it. We know how to do it because we've been developing with Zephyr a long time now, and just use the driver architecture. It'll standard way to do things. So we did this for our UWB module. We had to add support for the NXP SR040 UWB radio that's in our NX040 module. So here's a quick snapshot on the left-hand side showing the source tree for our new driver. We implemented some new DTS bindings, and then a couple C files for different layers of the API to talk to the radio. And then, because of device tree, we can easily add that new UWB radio in and attach it to the SPI interface here. And with those new DTS bindings, we defined our interrupt GPIO and the ready and reset GPIOs. So you do that, and now you have a standard way to access the SPI interface to the radio. Next, we need to be able to expose any C API we want to MicroPython. This is done with PYI files. So here's a quick snapshot of our UWB PYI. This is how we define a new API for MicroPython. We've got our init function, and then we can document what each of these does. And why that's nice is we have Python scripts to generate C stub code from the PYI file. That C stub code is used to do a lot of common code that's needed to integrate kind of the C in with Zephyr. And then also, that PYI file is used to generate our user-facing documentation. And then us at Ezurio, we were the C developers that implement that C to Python API here. So here's a quick snapshot of getting a new UWB session. So this function right here is equivalent to the Python new UWB session. So when a user calls a new session from Python, this is the exact function that runs. It goes and calls any internal APIs we need. It uses the MicroPython APIs to create a new Python object as seen down here at the bottom, and then we return that object. So then in Python you have access to that object to then further use it in your Python code. On the right-hand side is a quick snapshot of our user-generated API from that PYI file, so users can come in and look how to use the APIs and see what's possible when they're writing their Python code. And here's a quick link to that. Connectivity is first for us, as we are primarily a wireless company. We need all kinds of wireless connectivity. So Zephyr has a fully qualified Bluetooth stack. It's certifiable. It's up to date. We get all the networking we need, any protocol we can ever want. We get security with Embed TLS. And as I mentioned, drivers, modem drivers, Ethernet drivers, and LoRa and LoRaWAN. And it all works and it's reliable, and that's what Zephyr gives us. Back to the firmware updates, right? You can't do anything unless you can update your product in the field. So Zephyr has a solution for that as well with MCU boot. The MCU boot bootloader is supported in Zephyr. Along with MCU boot bootloader, there's the MCU manager, which is your protocol for communicating and updating an image over a USB or UART or BLE. And then also we are able to implement updates from the cloud, which I will get into detail shortly. So first, firmware updates over BLE. We use the SMP protocol that's built into Zephyr. SMP in this case stands for Simple Management Protocol, not Symmetric Multiprocessing. I know there's dual acronyms there, so it's confusing sometimes. With SMP, it gives you a standard way to do image management. Also, you can do file system management, which is great for updating your Python apps over BLE. And what's really cool is the SMP GAT service is always present no matter what the user's Python is doing. And we did that to make it easy, so the user doesn't need to know about SMP or how it works. Basically, if the user doesn't have a Python script on their board, by default, we have a default Python script that'll get up and run, start advertising, and make that SMP service available. So now you can connect to the device and firmware update if you wish. But if the user has their Python app written and they start up BLE and they're doing whatever they want with BLE, they want to advertise their own packets or their own, and then use their own GAT database to do whatever they want, that SMP service is still there in the background for use. And the user doesn't have to do anything. It's there to use, which is really nice. Firmware updates from the cloud are obviously very useful for managing devices when you have a bunch in the field. You can check out my last year's presentation. I went into a lot of detail about device management with Zephyr and lightweight M2M. We got the link here. So I'm not going to go into super deep detail on lightweight M2M, but we're using the Zephyr lightweight M2M client. We use Object 5 for a firmware update. This allows us to update the core firmware, which in case we add new features to the core, that's important. Then we use Object 9, the software management object, to update modem firmware in the case of our MG100. And also this gives us access to be able to update the Python apps themselves, which that's what the user is going to be writing. We have a 0 configuration sample running in Python, so all you have to do, you go to the sample, you load it on our MG100 or Pinnacle 100 dev board. It boots and runs with literally no configuration, and it will automatically connect up to the public LeSean server, and you can test out firmware update in 5 minutes, up and running. So what's really nice is the user can control lightweight M2M completely from Python. So we provided a lightweight M2M API from Zephyr, so we made the common functions a user would want to access available in Python. So if a user doesn't want to use lightweight M2M, they don't use it. And it doesn't start up by itself. They have complete control over starting it up. But what's great is the user doesn't need to know how the firmware update piece of that works. We've built that in under the hood, so when you connect and start lightweight M2M, Object 5 and Object 9 are already there for you, already configured, and you can send a URL to each of those objects, have the device download firmware, and it knows how to flash it and do everything. So just to highlight, over here's a quick snippet of getting lightweight M2M set up. You create a new object and give it an event callback, so anytime any relevant lightweight M2M event happens, you'll get a print message. But then you have control over setting it up if you were going to connect with security with a pre-shared key or not, or use bootstrap mode or not. And then also Object 3 in lightweight M2M is a required object, and that gives you information like manufacturer or firmware version and all that. So the user can set that up with these calls and set those fields in Object 3, wait for the network, and once you're on the network, just call lightweight M2M start, and it gets up and runs. That's how simple it is. From that point, Object 5 and Object 9 are there, and now you can update from the cloud. Furthermore, besides updating the core firmware, users need to be able to update their Python apps. We've created a Python tool that allows you to package up your Python app. So your Python app could be one or more Python files. So you need to be able to package each of those files into some container. And we chose to use a zip container with no compression. And each file is also, when it's packaged, a SHA-256 is used, so when it's extracted on the device, we can know if the file's valid and there's not corruption. And then you get your packaged, versioned Python app, and with Object 9, you can download and install it. So I'll just touch on device management real quick. Again, lightweight MDM is a really great protocol for device management, so we have that built into our gateway. Our partner EdgeIQ offers a platform for managing your fleet of devices. Alternatively, there's the open source Eclipse Lashan project if you want to try it out and even use it to do your own servers. So with all this, reliability, of course, is top of our list. So we have an automated test platform. And why I bring this up is because with MicroPython, you get access to the REPL. So now with all our devices, there's a standard way to command and control them. So we've built a lot of tests with Robot Framework, and we've built functions like you can see here, user REPL send. And now we can send anything over the REPL in a standard way. We can automatically load scripts and run them and then look at results. So all our devices support BLE. We can run all the exact same robot tests on any platform, and we don't have to keep developing new tests because there's different ways to talk to boards. It's all the same. So this gives us a lot of confidence, and we can distribute new releases with confidence and do it very fast. So now I'm going to take a look at writing some Python. So I'll spend a little time on this just to show you. It's a little bit readable. I'll kind of touch on everything here. So this is a complete application for doing a BLE peripheral. I'll just highlight that it's only 60 lines of code, and that's all you need to get a BLE peripheral going with a custom GAT service. So on the left-hand side, we'll look from top to bottom, setting up a name and the UUID for your new service. We have a connection callback, a disconnect callback, a callback for writing to one of the GAT service UUIDs, a little helper function here for doing UUID to bytes. We set up our GAT table with a JSON structure. So for those of you who know how BLE works, you define a service. You have a UUID for that main service. You can name it whatever you want. And then you can have one or more characteristics in your service. And you can define them as read or writable or both. In this case, we're making this service writable. As we move down the file here, on the right-hand side here, we call BLE init. That gets us the BLE subsystem underneath all initialized. We set up our peripheral callbacks. We want a connection and disconnect callback. Those are our functions over here, so we can print out a message. We know we're connected or disconnected. And also on disconnect, we can automatically start advertisements again, so we're discoverable. And then we have a function to set up the advertiser, right? Peripheral advertises. So we get access to that new object, stop it, kind of clear everything out. And then we have some nice APIs for adding to an advertisement. Advertisements work by length tag values. So in the BLE spec, there are certain tags that are for different fields in an advertisement. So right now they're just defined as numbers here, so it's not too friendly, but you can look in the BLE spec for what 1 and 7 are. But this allows us to customize our advertisement very easy, and we can have control over what physical PHYs we want to use. In this case, we're setting it up to use the 1 and the 2 meg PHY, so extended advertising, and our interval, and then we start up our advertisement. And after advertisement started, we can start up our GAT server. And now the peripheral's running and advertising and ready to be discovered. So then the other side is your BLE Central. Again, only 60 lines of code to get your BLE Central going to connect to that peripheral. And I'll breeze through this a little faster. It's very similar. The only difference is we have a scanner and a scan callback where the discovered device will get printed. And we have a send message, so we can send something over to that peripheral. And again, a connection and disconnection callback. And so we init BLE, we call our scan init function and start scanning. When we get a scan callback for the device we're looking for, we log that here and connect to the device. In our connection callback, then we're doing we're getting a hold of a GAT client object, so that way we can send a message over to the peripheral. And then it disconnects. So that's a really simple, bare bones example of both sides of BLE. And then we take it one step further, getting that data to the cloud. So you would build all that same stuff. In this case, a lot of times a gateway may only need to scan. So for our gateway, we implement our scan callback. So when we discover that device, we can do some Python code for filtering, and that's what you're seeing here. So we can keep track of if we've seen the device, and we create a dictionary to store the device's ID. When's the last time we saw the device, its message, and then we can do cool stuff like rate limiting it. So here on line 79, if we've seen this device already, too soon, we just return out. Otherwise, if it's been long enough, we can pull out the data from the advertisement, update our dictionary for keeping track of that device, and then add that data to a list. And then we have a timer that fires, and we can pull data out of that published list and send it up over MQTT to the cloud. So again, this is way faster to develop something like this than writing in C, because there's no setup time, and you can, with the Python language, it's a lot more powerful. Looking to the future, we don't have everything done yet, but we do have a pretty complete system, but we're looking into implementing threading in MicroPython by hooking into Zephyr threads, so you would get true threading in Python. Adding in support for a little bit more flexible firmware updates. So right now, the only way to update from the cloud is using lightweight M2M. We want to add a Python API that allows the user to write an image to the firmware update slot and make it easy for the user. So what that would allow the user to do is download an image from the cloud in whatever format they want, and then use a Python API to flash those bytes. And they don't need to care about where it's going, it'll just work. Also, we want to get some encrypted file system stuff going. Making sure your secrets are secure is important for IoT devices. We don't have all of BLE secure connections working yet. That's soon to be there, being able to pair. And then our friends at Memfault, they have a great platform for crash analytics and device metrics. We want to build some features into the core firmware for that. So in summary, development on devices with MicroPython is much faster. There's virtually no setup time. You download our extension in VS Code, connect to the board, and you're up and running. You don't got to compile any firmware, download any host tools in order to compile the firmware. You're getting production level code without writing anything in C. And last but not least, putting all the firmware pieces together in C is hard, right? We know this. We've had this feedback from customers time after time. And so we've done all that hard work to put all the pieces together, and they don't need to worry about that anymore. And that's it. Any questions? I'll highlight that Ezurio has we have a Discord channel on the Zephyr server, so I monitor that frequently, and you can get a hold of me there. We don't have a room host. He'll bring you a mic. Thank you.
Cool presentation, thank you. I played around with MicroPython Lava controller, and it's, at least for prototyping, I really liked it. But I had always a feeling that performance in the end was like 30, 40, 50% less. So did you have any like benchmark, how much it was like impacting the system?
We don't yet. We haven't needed to do anything where speed is a concern. I will say that I don't see any concerns with speed. I could see maybe if you're trying to do some really intensive sensor applications, maybe that's where you're going to run into problems. So we haven't got there yet, but I will say low power works, just because we get low power from Zephyr. And the execution time really doesn't seem to be that different, but yeah, we haven't fully benchmarked it yet. Good question.
Thanks, Ryan. Is there an escape hatch for Canvas users to implement or bridge the gap, the feature gap between Zephyr and what's exposed in MicroPython? Or do they just have to wait for Ezurio to implement it?
So right now, we're actively taking feedback, and we would implement it. We haven't open sourced this yet. There's no reason we can't. We just haven't taken the time to. We want to make this easier for people, so typically that would be a lot of work for someone, especially if they don't know Zephyr, so that's why we haven't.
Hi. A quick question around DFU. You mentioned that you guys are using MCU Manager and SMP. Mm-hmm. So what does it need to happen to get a package that runs CircuitPython, MicroPython, and DFU to devices running your platform? So right now, we're providing that core firmware image. It's not open source, so we will be rolling out new firmware updates, so we will provide the binary. The binary is already signed. So with our desktop tools and our mobile app tools, we already have a way to easily just put the binary on there, and it will flash it over BLE or over UART for the user. But it's using standard protocols like the MCU Manager CLI could be used manually. All right, anyone else?
When you say low power is working out of the box because of Zephyr, what sort of current draw are you getting with your SARA module, for example, as in the low power mode? Is it getting right down to the low power sleep? Yeah,
couple microamps now. UWB is very power hungry when you are in a session, but you have control over that from Python. If you're doing something, then you can shut down and tell the REPL to go to sleep, and yeah, there's no difference.
So you could use your SARA module to say periodically do a BLE TX packet every second, but then every now and again turn on the ultra wideband to do localization or something like that.
Yes.
If you were doing just that sort of once a second BLE transmit, but you can still achieve ultra low power.
Yes.
Yeah. Okay. Yep. Excellent. Okay, thanks.
All right. Anyone else? Thanks, everyone.